Hi friends, welcome to Unlock Layouts. In this video today we are going to discuss the topic of various kinds of matching techniques in VLSI layout. Let's start the video. So before watching this video, if you are new to my channel, please go and watch why we need to go for matching initially. So after watching my first video, then you can come back to the second video, matching techniques, and watch this video. Then you can easily understand what is matching and why we are going for matching and the kind of matching techniques. So usually in this video today I am going to discuss matching technologies associated with VLSI layout. So usually we have two types of matching techniques. First one is called interdigitization based matching and second one is called common centroid based matching. Let us discuss interdigitization based matching. So whenever there is a current related matching, whenever there is a current is our main concern, current is our, we have to give the importance to the currents. In such a situation we have to go for a interdigitization based matching techniques. Usually current mirrors, resistance, capacitance, all these three devices will be done by the methods of interdigitization based matching and then common centroid based matching. Whenever there is a VGS and then VT is a main concern, we have to give importance to VT and as well as VGS. So in that situation we have to go for a differential pair matching, and then current mirror, resistance, capacitance also can be done with a common centroid pair matching, but differential pair compulsory, it should be done with common centroid matching only. So these are all the two types of matching techniques we have, one interdigitization and one more thing is common centroid. So first we will go for a interdigitization based matching techniques. See, as I said, whenever there is a current related constraints or current related concern, we have to go for a interdigitization based matching techniques. And interdigitization matching techniques, it can reduce the process variation introduced by the manufacturing or else error introduced by the process variation. In x directional we can reduce the process variation. I will tell you how. First we will go for a one simple logic circuit. See, we have a two transistors. Consider these two transistor inputs are different, A and B. Two transistor inputs are different, but output we are taking from the two transistors common output. So in this case transistor Q1 and transistor Q2, two transistor we are having, inputs are different, both the transistors are getting the input from the different sources, but the output is common from the each transistor. So in this situation we need to turn on and turn off the transistor at the same time, since we have give the importance to the output, because the output is based on the Q1 transistor output also and Q2 transistor output also. The output is mainly based on the both transistor outputs. So we have to consider Q1 also, we have to consider Q2 also, but as practically each and every MOS transistors, it is not identical transistors. Even though if the transistors are fabricated in a same die, same kind of doping and same kind of technology, everything is same, but the each and every individual MOS transistors or transistor, that is not having the same kind of the behavioral wise and operational wise and performance wise, due to the etching related problem and due to the ion implantation related problems and due to the so many process variations or error introduced by the manufacturing time. All the transistor will have different VT, different performance, different behaviors. But in our situation, Q1 transistor and Q2 transistor has to turn on and turn out of the same time, but as practically it is not possible because of the process variation, and somehow we need to turn on and turn off the transistor at the same time. So that is why we are going for the technique called matching. First we will go for a interdigitization based matching. I have a is equal to 2 multipliers and B is equal to 2 multipliers. If you want to know what is meant by multipliers and fingers, I will add the separate video for multipliers and fingers, and then you can watch that video and get the idea from them. For time being I am telling, so A is equal to 2 multipliers, B is equal to 2 multipliers, which means we have totally 4 devices we have. These 4 devices has to be turn on and turn off at the same time, but practically it is not possible because of the process variation. Somehow we need to try to reduce the errors, or else somehow we need to make sure both the transistor A and B on and off time should be equal, or else we should be make nearby to the equal value. So if it is not possible 100% we can't reduce the errors, or 100% we can't reduce the delay from the each transistor, but somehow we need to try to reduce the delay. So we will explain with the one simple graph method. Consider x and y. So this is called V in of the transistor, this is called V out of the transistor, or else you can consider this is the input and output response graph, input and output response graph. How much time the transistor is taking, if the input signal is applied to the gate, how much time the transistor is taking to switch from on stage to off stage, or else off stage to on stage, or else how much time it is taking to give the output whenever we are giving some input signal. So this is related to time domain. So we'll go for a domain, time domain. A is equal to B, B is equal to 2, B is equal to 2 in the sense, suppose without matching, if we are placing the transistor, so this is A1, A2, B1, B2, consider A1, A2 and then B1 and then B2. So as I said, A is equal to 2 multipliers, B is equal to 2 multipliers. So what will happen? The first transistor is the one will turn on initially. For example, this is turning on at 1.1 millisecond, and second transistor turning on at 1.2 millisecond, and third transistor is turning on by 1.3 millisecond, fourth transistor is turning on by 1.4 millisecond. See, A1 transistor is turning on in a different time, A2 transistor turning on with a different time, B2 turning on with a different time, and B1, B2 both is turning on at different time due to the process variation. So what average time of the A is equal to 1.3 seconds, right, and average time of the B is equal to 1.7 milliseconds. See, the first transistor turning on at 1.3 millisecond and the B transistor is turning on at the 1.7 millisecond, or else we can consider, suppose if you are giving the input to the A transistor, we will get the output after 1.3 millisecond delay. Same, if you are giving the input to the second transistor, B transistor, we are getting the output after 1.7 millisecond delay. So these delay, this is not acceptable ratio. We have to make sure, or else we have to try to reduce the delay between these two transistors as closer as possible. So without doing matching, if you are placing the transistor A1, A2, B1, B2 and start your routing, these errors will be introduced. Same situation, we are going for a matching based technique. So matching in the sense is just a pattern. So we can same time domain, same x and y input and output ratio. See, instead of placing A1 transistor, A2 transistor, B1 transistor, B2 transistor in such a fashion, we have to replace, or else we have to rearrange the pattern. So initially we have A1, A2 and then B1 and then B2. So this is the pattern for earlier. After doing matching, we are rearranging the pattern. Example A1, B1, B2, A1. So this is my second pattern. So here I am placing all the transistor in such a fashion. See, this is A1, this is B1, this is B2 and this is A2. Just I am not doing anything. All the fabricated mass are different characteristics. I didn't do any fabrication related issues. I am not handling with the fabrication related techniques or nothing. Just I am rearranging the transistor in this fashion. Same first transistor will turn on at 1.1 second, B transistor will turn on at 1.2 millisecond, same this can consider 1.3 and same this can consider 1.4. See, 1.1, 1.2 and then we can take it as a 1.3 and we can take it as a 1.4. So average time of these A 1.1 plus 1.4 is equal to 1.5 and average time of these B transistor B is equal to also 1.5. See, 1.2 plus 1.3 is equal to 1.5. Before, without matching, we are placing the transistors in a normal way. the delay introduced by the transistors and the on and off time introduced by the transistor, we are facing some delay here, but here we are not handled any kind of new techniques, no fabrication related techniques, no routing related techniques, nothing, just we are replacing the transistor, we are just changing the pattern of the transistor. By changing the pattern only, we almost exactly we achieved 1.5 both the transistor turning on and turning off at the same time. Or else you can consider input response from the A transistor. Suppose we are giving the input to the A transistor, we are getting the delay output after 1.5 millisecond. We are giving the input to the same B transistor, we are getting the output after 1.5 millisecond. So both the transistor on and off time, it is equal. So this is the reason primarily or mainly why we are going for matching. So matching have so many patterns and so many techniques. So usually this is only one direction, see, x direction and y directional, we have two directionals. We are reduce the errors introduced by the fabrications or introduced by the process variation only in x direction. So that we are not handling with the y direction, only one direction we are what do you say, we are reduce the error. So this is mainly called interdigitization based matching. See, one A device and then one B device and then one B device and then one more A device. So it is interdigitization, not equally, this is interdigitized, one upon one, shuffled, we are placed in this fashion. So this is normal pattern without any matching. So this is not acceptable. Why this is not acceptable? In the sense, because of the normal layout pattern, the transistor itself introducing some delay. So we are reducing the delay, just rearranging the pattern. So this is called interdigitization based matching, or else this is the reason particularly why we are going for matching. So this is just a graph wise. If you understood this, then second video or else second slide I will tell you based on the transistor structure. See, same, we have 4 transistors. So we have 4 transistors, as I mentioned, this is A1 transistor, this is A2 transistor, this is B1 transistor, this is B2 transistor. All the transistor gates are connected. See, this is a gate input signal we have given to some other input node. So due to sheet resistance of the metal or else due to distance between these two transistors, so in this particular point we are giving some input voltage, due to RS of the metal we will lose some voltage, we will lose some voltage. So that is the reason why the first because the voltage is coming by this way, it will go to the first transistor, after few seconds only it will reach the second transistor. So that's why the process variation is here happening. And one more thing, not only for the routing related issues, and it is also associated with the etching related issues with the each and individual transistor. As I said my first video, all the transistor, 4 transistor, if the 4 transistors are fabricated in the same time, same foundry, same technique, all the transistor etching will not be uniform, etching will be differ from the each and every transistor. Due to etching also the transistor performance and VT may vary, due to routing also the transistor performance may vary. So things, so many things are there to turn on and turn off the transistor, or else the related to delay, so many things associated with the delay, not only routing, not only doping, and not only what is a ion implantation, so many things, it's all related to fabrication process. But just we are replacing the transistor A1 here and then B1 here, B2 here and then A1 here. See, now we are giving the routing to the all the transistors. So we are giving routings, 1 second. So now somehow we reduce the error introduced by the transistors. So now A1 and A1 we have to give parallel routing. Sorry, my drawing is not good enough, just try to understand. See, A transistor input 1 via, this is metal 1, this is metal 2, same, 1 sec. See, same transistor we are maintaining equal or else parallel routing. So by based on the parallel routing, see all the side, left and right side, if you consider a mirror, the mirror kind of connection, left x direction, x side and y side. So consider this full area as x side and this full area as a y side. So x and y, here I am giving parallel routing, and the VT also changed because of the fabrication process. The VT will change, even though there is a problem with VT. While doing the parallel routing, first I maintain the equal parasitics from the A device and B device, which means x side and y side. And also if the patterns are shuffled and we are just rearranging the transistors, then what the process variation or error introduced by the fabrication time, that errors also here I am reducing. This is the main reason for the why we are going for the pattern or why we are going for matching. Let's explain with one proper schematic diagram. See, consider same two transistors. So two transistor source are connected. So this is source and this is source. This is drain and this is drain terminal. So output is different. So this is going to some other net x value. This is A and this is B. So we have A is equal to 2 multipliers and B is equal to 2 multipliers. So as I mentioned, so first we have to choose for the better pattern, best pattern. So pattern in the sense, first we have to already, for example, A1, A2, B1, B2, if you are placing in without any matchings or without any proper pattern, then we will get the delay in between the two transistors. So that's why we have already chosen the pattern. So pattern A1, B1, B2 and then A1. See that source and drain terminal, what do you say? So each A and B drain terminals are different, but the source are getting shorted here. So in this pattern, this is a drain terminal, this is a source of A1, this is a source of B1, this is the this is a source of, sorry, this terminal should be drain of the B1, this is also drain of the B1, and then if it is drain, this is source and source, this is drain. So the first transistor having one drain terminal and source terminal. A transistor source is already shared with B, so B, and the B transistor drain and drain is already shared, and one more source and A source and B source is already shared. This is a drain terminal. Again we are merging these two contacts. Again one more source, this is a common source for A1 and then B1, this is a common source, this is a common drain for B1, because B1 B2 having the same drain, right, because multiplier is 2, so the drain should be shared. And then here we have a A2 transistor. Suppose if it is a drain, it should be on source. So A transistor, B transistor, source are shared, and then drain transistor. So what is a drain terminal? So gate we can give the individual connection, but drain, how we have to give the drain connections? From here to here we have to route on normal metal. See, since the two different drains, so this is A drain, this is A drain, and this is one more routing single line, this is B drain, and source terminals are already shorted, right? So source and source terminals are shorted, and we can give this is as a and B common X output. So X output is here I mentioned, right? So in this area I mentioned this is X terminal, X net, so this is X net. So this is how the transistors are merging with the interdigitization based pattern, and how the source and drain connections are we are giving, and we are implementing with the new pattern what we have chosen. And as per my experience I am telling, this is not a best pattern. If there is any source terminal or drain terminal shared nets are there, then we can go for this pattern. And one more thing, A is equal to 2 and B is equal to 2, we are not only having A B B A pattern, we have so many patterns. So many patterns in the sense, I will draw the pattern. See, A, B, B, this is one pattern, and then A, B, this is one more pattern, B, A, this is one more pattern, or else we can go for A, B, A, one more pattern, and then we can go for B, A, B. So likewise we can draw n number of patterns. The pattern should be mainly considered based on the schematic. Based on the schematic diagram only, we can go for which pattern is the best pattern and which pattern is it is fulfilling our desired operation or desired function of the circuit. So we have a n number of patterns, but choosing the pattern, it is 100% based on the schematic only. See, based on this schematic only, here I am chosen ABBA. So this pattern is the best pattern because of this schematic. So because we are source and drain source terminals are shared here, so easily I can merge source and source terminal, then I can reduce the distance between the transistor, I can shrink the area without affecting the performance of the channel. So the pattern, choosing the pattern is mainly based on the schematic diagram, and schematic, based on the schematic only we have to go for the pattern. So these are all the patterns we have for a interdigitization based pattern. So whenever there is a current related problem, we should go with the interdigitization based pattern. And then now we are going for a common centroid based pattern. So now we have to handle common centroid based pattern. So whenever, as I said, there is a VGS or VT, so these two things are constrained, we have to go for a common centroid based pattern. In common centroid based pattern, the process variation introduced, what is a error introduced by the process variation, can be dissolved or can be solved both x and y directional. In earlier we have only one quadrant, we have only Q1 quadrant. Consider this is Q1, this is Q2, and then this is Q3, and this is Q4. So in without common centroid, no, we are handling with the interdecision, we handled only Q1, which means one directional. We didn't try to reduce the what is the process variation in the y directional, only we reduce the process variation in x direction. Whenever we are coming to the common centroid, we have to handle, we have to try to reduce the errors in both x and y directional. Here we have to draw one more circuit. See, we will go for a differential pair. So this is one input, this is another input, the source terminals are shorted together, this is source terminal, and drain terminal, this is the x1 output, this is the x2 output, this is A transistor, this is B transistor, this is A1 input, this is this is B1 input. So A1 input, B1 input. So here we have A is equal to 2 multipliers and B is equal to 2 multipliers. We have totally 4 devices, and this is not, we can't implement the same pattern with interdigitization. We have to reduce the process variation by x and y directional. So here I will tell you the patterns. So A and B, so we have to make first one coordinate. So first A transistor, then B transistor, and then B transistor, A transistor, and B, A, here also A, here also B. See, this is one pattern. Here I am drawing the patterns. See, I have a n number of patterns, even I can go for n number of patterns, AA, BB, BB, AA. This is also one pattern. Then A, B, B, A, B, A, B. This is also another pattern, and one more pattern. Entire A should be upside. Entire B, 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 B. So this is also one pattern I have. So AB, AB, BA, BA. This is one more pattern, and then one more pattern A, B, B, A, again A, B, B, A. This is one more pattern. Still I can go for a n number of patterns. I can go for maximum, I can go for a n number of pattern, but as per this schematic I am drawing 6 patterns. So based on these 6 patterns, we can't ensure which pattern is the best and which pattern is the worst. Based on the schematic diagram only we can go and we can choose for these patterns. Among these 6 patterns we have to choose the best pattern based on the schematic. First based on the schematic, and then second one, what is the frequency handled by the circuit, and what is the voltage, which means VGS, what is the voltage, current rating and voltage rating of the transistor, and what is the input output frequency of the transistor. Based on the frequency and based on the transistor performance only, we have to go for which pattern is the best pattern. And as per my knowledge, so we can go for this pattern. As I said, no, this pattern is the best pattern. And one more thing, so we can, as I said, this is the best pattern as per my experience, and this pattern also we can go, which means AB, not AB, AB. So this pattern AB, BA and BA, AB. See, we can draw one graph. See, first transistor, so we will go for this pattern ABBA and BAAB. So first transistor A and B, so we can derive for the quadrant. See, this is a quadrant, so we will draw here A, B, B, A and then B, A, B. See, we have a X and Y directional. See, so this is a mirror image. So these B and these B, both these B on and off time in between equal area is here. On and off time should be here. This A and this A on and off time should be here. From this A to this A on and off, it's on the same area. From this B to this B, distance between these two B, it is in the same area. See, all the transistors A and B transistor leading in the same area. So here somehow we reduced some process variation introduced by errors introduced by the process variation. And one more pattern also we can go, A, B, AB, AB, then we will go for a BA, BA. See, the first consider A1, A1, A2 and then this is A2, because both transistors having 2 multipliers, right? A is equal to 2 and B is equal to 2. So, or else we can go it for A is equal to 4, B is equal to 4. So, this pattern, I am sorry, this pattern is A is equal to 4 and B is equal to 4. So, A is equal to 4, B is equal to 4. See, the common center point between this A is here and B also here and A also here and B also here. Everything laid in a center point. All the transistor on and off time or all the transistor leading in a center point of this area, both X and Y directional, we reduce the process variation. So, this is common centroid based process variation. So, whenever we have a VGS voltage VT or VGS based related pattern, and whenever we are handling with that one, we have to go for a common centroid based pattern. So, as per my knowledge I am telling. So, this is A is equal to 4, B is equal to 4. Suppose A is equal to 2, A is equal to 2 and then 1 second, I don't know, something wrong. Suppose we have a pattern of A is equal to 2 and then B is equal to 2. We have to draw for X and Y directional. See, A, B, B. So, this is the best pattern. So, the common point between this B and this B is here and this A and this A is here. So, somewhere here. So, this is common centroid based matching. So, we can go for a based on the multipliers and based on the fingers of the circuit. So, we will get it A is equal to 6 and B is equal to 6 and then A is equal to some value and B is equal to some value, X and Y value. So, based upon the devices, based upon the A and B, we have to choose the pattern, and based upon the frequency of the circuit, how much frequency it will handling or what is the input and output voltage, based upon that one also we need to give the importance to the pattern. So, this is called common centroid based pattern. See here, as I said, A is equal to 2, A is equal to 2 and B is equal to 2. So, common centroid based matching here, we are handling with common centroid based matching. A is equal to 2 and B is equal to 2. So, the first transistor, this consider this is a transistor as per my pattern. So, what is the pattern I drawn here? For example, A, B and then B and then A. So, what we have to do? Source terminals are shorted. So this is source terminal, this is source terminal. So A source and B source are shorted. So this is a drain of the terminal. So source and source terminal. This is a drain of the second B1 transistor. This is A1 transistor. So this is B2 transistor. This is A2 transistor. This is also source terminal, drain terminal, drain terminal. So this is the 4 transistor terminal. We are merging the source terminal common here. Here also we are merging the source terminal common here. There is a drain terminal, drain terminal, drain terminal, drain terminal. Gate remains same. So we are not giving any connection to the gate. So what? After finishing the layout, we can take it as a common source. Easily we can finish the routing by adding metal layer here. So source is connected. So source net, we can call it as this is a common source, and A drain and B drain. So this is the A transistor, this is A transistor, this is B transistor, this is B transistor, right? So this drain and this drain has to be connected. So we have to give the routing according to this, and we have to connect this drain and this drain separately, and the drain terminal. See, this is a drain terminal, this is a drain terminal. So drain terminal we are taking as an output terminal. So this is common centroid based matching, because in only one directional, we are not handling with only one directional, we are handling we are reducing the error both x directional also and y directional also. X and y quadrant, we are reducing the process variation. So this is called common centroid based pattern. I hope you like this video, and I hope I have cleared the doubts what is matching and why we are going for matching. And if you like my video, please click the like button. Please subscribe my channel. If you have any doubts, please contact us to my email ID and follow us on my Facebook page. Please share my video to your friends so that they can able to understand what is matching, and thank you for watching my video.